In today's class discussion, we'll be talking about circular motion. As I go through the circular motion class discussion, you can see it's already filled in, so I apologize if that upsets you that the answers are already visible. But my goal is to try to keep these videos as short as possible, but at the same time deliver some good physics content and that you understand whatever the class discussion is about. So today we're dealing with circular motion, and basically circular motion is dealing with objects moving in a circle, and in this class we primarily deal with something called uniform circular motion, which basically means that the speed is constant but its direction is constantly changing, if you will, because moving in a circle. So it has a changing velocity, which I mentioned here, changing velocity, but the speed is constant. So it'll be saying, we may say it's going in a circle at like 10 meters per second. It's moving around a circle at 10 meters per second. But because its direction is changing, it therefore must be accelerating. Okay, it must be accelerating. If you think back to what the definition of a velocity, or what a think back to the definition of velocity. Velocity is a vector quantity, and so that means you have a magnitude and a direction associated with it. So keep in mind, all objects undergoing uniform circular motion are actually accelerating, even though their speed may be constant. This type of acceleration, as I mentioned in the document, is referred to as centripetal acceleration. So we come to our first question. If a car is accelerating, is its speed increasing? Well, it could be. The speed could be increasing, but when we're dealing with uniform circular motion, the answer is basically the speed is constant. Okay, it's always going to be the same. The thing that causes it to accelerate is the direction is changing. So it is accelerating. It's just not kind of how we've been talking about it previously in other chapters, where an acceleration was usually speeding up or slowing down. In this case, the direction is changing. One key concept, and it's something that I'll ask you over and over again in various worksheets, quizzes, and whatnot, is what is the acceleration direction? Okay, if I draw an object undergoing circular motion, what is the direction of the acceleration? And the acceleration is always pointed towards the center of the circle, always. Okay, so if I ever ask a question about that, it's really actually a very easy answer. You just draw an arrow pointing to the center of the circle, and I've got an example of that later on in this document. To figure out the magnitude of the acceleration, to get actually a numerical value, we're going to be using this equation right here. A centripetal, or the centripetal acceleration, equals the velocity squared over the radius. It's a formula that you will use quite often in this chapter, so make sure you make a mental note of that or write it down someplace, because it's something we use a lot. Acceleration centripetal equals v squared over r. Alright, in the diagram below, there's a question anyway. In the diagram below, a car travels clockwise at a constant speed in a horizontal circle. At the position shown in the diagram, which arrow indicates the direction of the centripetal acceleration of the cart? Well, if you remember up here where I have the two stars, the centripetal acceleration is always directed towards the center of the circle. And so which arrow would represent that? Well, that would be arrow A, because that's pointing towards the center of the circle. Second question, the diagram shows the top view of a 65-kilogram student at point A on an amusement park ride. The ride spins the student in a horizontal circle of radius 2.5 meters at a constant speed of 8.6 meters per second. The floor is lowered and the student remains against the wall without falling to the floor. So basically it's one of these rides that just spins you around pretty fast. It says, what vector represents the direction of the centripetal acceleration of the student at point A? And here's the student at point A. Well, don't think too hard. The acceleration is always pointed towards the center of the circle. So with all these arrows here, what choice would be towards the center? Well, it would be choice 1, which is circled for us right there. Here's another question. A car rounds a horizontal curve of constant radius at a constant speed. Which diagram best represents both the car's velocity and the acceleration? This maybe will involve a little bit of explaining here. The acceleration still is always directed to the center, so there's the arrow pointing towards the center. But the velocity vector is always what's called tangent to the circle. Tangent to the circle. And basically what that means is one point touches the circle and the other just kind of like shoots straight off. So here is the velocity vector. It's just going to be pointing straight off of the circle, and it does connect here at this point. If I were to draw another circle, and let's say we're moving in a clockwise fashion like this, and we have an object here, if I were to draw the velocity vector as this object moves in the circle, the velocity vector would be, again, tangent to the circle, just be like this. Or if I had a point here, it'd be like this. Okay, so basically it's like if it were to stop moving in a circle at that instant, what direction would the object continue to move? And I think if you use just kind of common sense, you would think, oh, well, just keep going straight. Maybe that isn't common sense, but just, I think if you think about it, that kind of makes sense. Oops, that was a little fast. Let's see here. Question. A 0.5 kilogram object moves in a horizontal circle with a radius of 0.25 meters at a constant speed of 4 meters per second. What is the magnitude of the object's acceleration? All right, so here I've worked the problem out for you already, so I'm sorry it loses a little bit of the thunder of asking these types of questions, but this is the formula that you're going to use. A equals v squared over r. This was mentioned earlier in the document. They give me the velocity right here. They say speed, but it's kind of the same thing here because basically we don't really have a direction when we're talking about circular motion per se. So our velocity is 4 meters per second, and the radius is 0.25 meters. Okay, there's the radius. So you're just going to take 4 squared divided by 0.25, which you can see my math right here, and that gets you an acceleration of 64 meters per second squared. You'll notice the accelerations in this chapter are much larger than some of the accelerations we've been dealing with in previous chapters, and that's perfectly okay. So if you're like, geez, that seems like a huge number, it's probably okay. The accelerations for uniform circular motion tend to be higher than previous chapters. So we've talked about acceleration so far, and we've hit on speed, but we haven't really given you a formula for speed. The formula for speed is really what it's always been. Speed equals distance divided by time. The problem is when you talk about a circle and we're referring to the distance, well, we're talking about if you go around this circle one time, that is the distance, right? I mean, usually that's how we measure it, is how long does it take to go around a circle once? Well, then the distance basically becomes, we need to calculate the circumference of this circle. And here's the formula for circumference. Hopefully that isn't foreign to you, but circumference equals 2 pi r. So another way of actually writing this formula would be v equals 2 pi r over the time it takes to complete one path around the circle. Because this is the distance, right? This 2 pi r is the distance that it travels divided by the amount of time it takes to do that. So just kind of keep that in mind. It's really the same stuff we've been doing. It's just now we're talking about something that's moving in a circle instead of moving in a straight line. So here's a question for you. Miranda drives her car clockwise around a circular track of radius 30 meters. She completes 10 laps around the track in 2 minutes. Find Miranda's total distance traveled, average speed, and centripetal acceleration. Ooh, this is a biggie. Alright, the first thing I start by doing is I wrote down my formula for circumference. Circumference equals 2 pi r. And the reason why I chose that is because I want to know what is the distance that Miranda travels to go around the track once. All I know about the track thus far is that it's a radius of 30 meters. So I just plug that in where it says r. So take 2 times pi times 30, and that gives you some number. Now I kind of jumped ahead here a step because it says she goes around this track 10 times. So I multiply this quantity by 10. So that must be about 188 meters to go around once. So 188 times 10 is about 1,884 meters. Hopefully I didn't lose you here in the math, but basically once around the track would be about 188 meters, but she goes around it 10 times, so I'm going to multiply that by 10. Then I say to myself, this is the total distance traveled right here, 1,884 meters. How long did it take her to go around the track in that amount of time? Or how long would it take her to go on the track or travel this distance? Well, the answer is 2 minutes. It tells us that the time is 2 minutes. The thing is, though, usually with speeds, we want it in seconds. So I'm going to change that 2 minutes to seconds. So I'm going to take 60 times 2, and that gets me my number right there where it says 120 seconds. 60 times 2 is 120 seconds. Okay. So I'm going to take 1,884 divided by 120, and I'm going to get a speed of 15.7 meters per second. So far, I've calculated my total distance traveled, there it is, my speed, and the last thing they want us to do is calculate the centripetal acceleration. And so I'm going to, once again, take out my formula, A equals v squared over r. My v, or velocity I should say, is 15.7, and I'm going to square that. Don't forget that. A lot of times people will forget to square the number. 15.7 squared divided by the radius, which that's given to us in the problem. It's 30 meters, and so I wrote that right there. So 15.7 squared divided by 30 gives us an acceleration of 8.2 meters per second squared. So keep that in mind as you work through these problems. Hopefully this isn't anything, like rocket science for you, but this is, so far what we've talked about is speed, distance traveled, and acceleration. What about centripetal force? if an object is traveling in a circle, there has to be a force applied to that object to keep it in circular motion. All right. Remember, if there's an acceleration, there must be a force. And so in a lot of these problems, we are calculating there's an acceleration. What's interesting is the centripetal force isn't really a new force. Okay, I don't want you to think of it as new force. Instead, the centripetal force is provided by one of the forces we've already talked about. It could be gravity, it could be tension, it could be an applied force, it could be even the frictional force. Okay, just for example, the Earth stays in orbit around the sun due to the force of gravity. Okay, the centripetal force is being applied or supplied by the force of gravity. That's why we stay in orbit around the sun. Without gravity, we'd fly off into outer space. Okay? If you take a bucket and whirl it around attached to a string, the string itself is what's applying the centripetal force, and we call that a tension force. Okay, so kind of keep that in mind. Centripetal force isn't so much a new force, it's a name that we give this force that causes objects to move in a circle, but there's typically a different force that supplies the centripetal force. I know that sounds complex at first, but just spend some time thinking about it, and hopefully it'll make some sense. Something else to kind of keep in mind is, and I mention it right here, the centripetal force is always perpendicular to the object's motion. The centripetal force is always perpendicular to the object's motion. So therefore, since it's perpendicular to the object's motion, it can do no work on the object, and what that really means for us is it doesn't make the object speed up or slow down. Okay, it doesn't make the object speed up or slow down, and that's why all these problems, the speed stays the same, it's just that the direction is what changes. All right. So hopefully this is a blast from the past. Here's Newton's second law, F net equals ma. Another way that you could look at Newton's second law is F centripetal, or again it could be F net, equals m times v squared over r. Where did I get this v squared over r? Well, if you think back to the formula for acceleration, acceleration is v squared over r. So all I did was I took this a and I plugged those letters in for a. All right, let's try an example problem and see what this might look like. An 800 Newton running back turns a corner in a circular path of a radius 1 meter at a velocity of 8 meters per second. Find the running back's mass, centripetal acceleration, and centripetal force. Okay, first, to get its mass, this is really some stuff from like chapter 4. Here's the formula for weight. Okay, weight equals mg. They give us the running back's weight. He's 800 newtons. I know little g is 9.8, so I'm going to take 800 divided by 9.8 to get a mass of 81.6 kilograms. And I just have a feeling we're going to be using this somewhere else in the formula or in this problem, so I'm going to put some stars by it to help remember that. So we got the mass, check. What about the centripetal acceleration? Well, acceleration equals v squared over r. The velocity of this guy is 8 meters per second, and the radius is 1 meter. So 8 squared divided by 1 is 64 meters per second squared. All right, so that's the acceleration. Check. Now, to get F net, or the centripetal force, I can either use this equation, m times v squared over r, or I can just use F net equals ma. Either one will get you the same answer. In this case, I use this one right here, F net equals ma, just because it's one less term. So I take the mass that I calculated earlier, 81.6, and there it is, times the acceleration, which I calculated earlier, 64. If you take 81.6 times 64, you should get an F net of about 522 newtons, and that is the centripetal force acting upon this running back. All right, onward and upwards. Last problem. The diagram below shows a 5 kilogram bucket of water being swung in a horizontal circle of 0.7 meter radius at a constant speed of 2 meters per second. The magnitude of the centripetal force in the bucket of water is approximately what? Okay, well, here we have this bucket being spun around in a circle, and we know some things, right? They tell us that the radius is 0.7 meters and the velocity is 2 meters per second. I just write that stuff down because I kind of like to do that. With those numbers, I can actually calculate the acceleration, and acceleration equals v squared over r. The v is 2, so I'm going to take 2 squared divided by the radius, which is 0.7, and if you do that math problem, 2 squared divided by 0.7, you should get an acceleration of 5.7 meters per second squared. Okay, so now we got the acceleration. What about the centripetal force? Well, if you think back to Newton's second law, F net equals ma. The mass of this bucket is 5 kilograms. which is just gotten from the problem, it's right here, divided by, times the acceleration, which is 5.7 meters per second squared. So here I wrote it down. Here's Newton's second law. The mass is 5, the acceleration is 5.7. 5 times 5.7 is 28.6 newtons. That takes care of this class discussion. Hopefully it helped you a little bit with circular motion. If you have any other questions, feel free to see me in class or shoot me an email. We'll see you guys later.